Dear reviewers, we are
Diane Ruge
and Michael Nitsche, and we are the PIs of Project A06. The physiology of extinction includes complex interplay between diverse brain areas, such as prefrontal, hippocampal, and amygdala interactions. The causality of these interactions for cognitive performance has, however, not been explored systematically. Furthermore, beyond this anterior network, also cerebellar areas might relevantly contribute. In our project, we will explore larger network interactions, including anterior-posterior communication, important for fear extinction. We will develop brain stimulation protocols suited for targeted stimulation of the respective involved areas. Use these protocols then to explore the causal relevance of respective areas for extinction learning, and explore the relevance of serotonin, a new modulator crucial for extinction learning, supposedly via its impact on long-term potentiation, the physiological derivate of memory formation for extinction learning. In the following, we will guide you through the studies of this project.
We will use a combination of EEG and fMRI during fear extinction to analyze this interaction. EEG is a method where you can record the electric currents, so-called oscillations, from superficial brain circuits. These produce brain rhythms which different remote areas in the brain use for communication. fMRI, the second method, measures oxygen use and thereby activity of brain circuits and is also suitable to reach deep brain areas. These methods will allow us to understand the task-related activation of and communication between the anterior network and the cerebellum relevant for extinction.
Having defined brain areas which form connections during extinction learning, we aim to explore the causal relevance for performance in Project B. For this, we'll apply non-invasive brain stimulation. This alters brain activity and connectivity. If task-related brain physiology is synergistically modulated by brain stimulation and results in respective performance alterations, this is a clear hint for causal relevance. For this task, we will develop brain stimulation protocols able to induce specific alterations of respective target areas. We will develop such brain stimulation protocols. This will include transcranial direct current stimulation, which induces neuroplasticity in the human brain, and transcranial alternating current stimulation, which modulates oscillatory brain activity and respective interareal interactions. We will define promising stimulation electrode positions for stimulation of medial and dorsolateral prefrontal cortex and cerebellar hemispheres and deep nuclei relevant for extinction learning.
So these are electrodes we will use that belong to the electrical stimulator, and we know that the position of these electrodes on the head influence the intensity of the current in the brain. By using modeling approaches, we will calculate with which electrode montage we can be most efficient, meaning yield specific and strong effects in our target areas. We will test the effects of this modeled stimulation on the physiology, and here we will use fMRI and TMS EEG. In the next study, we will test the causal relevance of task-related activity in the anterior network and the cerebellum for extinction learning.
If respective stimulation of single areas and networks alter extinction, and this is a clear hint for the causal relevance of these areas and connections. Beyond behavioral testing, we will also monitor respective physiological effects via fMRI and EEG. The last study of this project encompasses the relevance of serotonergic activation for prefrontal impact on extinction learning. Having identified the causal contribution of the prefrontal cortex to extinction learning, we aim here to clarify mechanisms. We have already shown that serotonin enhances TDCS-induced long-term potentiation, and the TDCS-induced long-term potentiation enhancement improves memory formation. We suggest here that serotonin improves extinction learning via strengthening of prefrontal long-term potentiation. We will test this hypothesis by exploring the combination of prefrontal TDCS with serotonergic enhancement on extinction learning. If serotonergic enhancement improves extinction learning via its impact on long-term potentiation, we expect superior effects of the intervention combination on respective performance. This is not only relevant for basic neuroscience, but could prospectively also be informative for future therapeutic application, for example in phobia.
To summarize, at the end of this project, we'll have understood the causal physiological mechanism underlying extinction learning in humans at the whole brain network level, with an emphasis on the cerebellum anterior network interactions. We will understand the role of neuroplasticity for and the impact of neuromodulators on extinction. These results will further pave the way to develop targeted interventional approaches for extinction pathology.
Bye bye.
Bye.